Okay. I hear myself. Is it okay now? Still hear myself.
Yeah.
Okay. They can hear me, right?
I think so.
Okay.
Yeah, as long as
Great.
you're opening mic on your laptop.
Okay.
Yeah.
Should I start?
Okay.
Yeah. What? Oh,
Okay.
sorry. Yeah, thank you. Hi, everyone. I'm Fatma. I'm an assistant professor at Koç University in Istanbul, Turkey. And I think it's good that I have the experience of teaching to sparsely allocated rooms. I don't know if you heard, but there were some protests in Turkey, and teaching this semester was looking exactly like this. So I am prepared, no worries. I will first talk about ETA, efficiency through thinking ahead. This is joint work with Open Drive Lab. My student Shadi started this project during his internship at Open Drive Lab. Chongka was also involved. Honggang also from the organizers was involved. So large models are everywhere, right? We see that LLMs, multimodal foundation models, are widely used in all kinds of tasks, including self-driving. Why is that? Because they are trained on large amount of data with billions of parameters, and then we can observe very strong performance and impressive generalization capabilities, not only for perception, but also for action, reasoning capabilities, and so on. The problem is that they are extremely slow, especially when we combine them with complicated reasoning techniques like chain of thought reasoning, right? In the current state, when you use a large model like this, we have no hope of achieving real-time requirements and self-driving. They're extremely slow. So in this project, we were thinking, how can we use these large models efficiently for self-driving? We want their capabilities, we want their reasoning capabilities or their contribution to perception and so on, but we also don't want to give up the real-time requirement. So the question here is, can we actually use these large models for self-driving while still adhering to the real-time requirements? Before we start talking about efficiency, let's do a small thought experiment. Let's forget about efficiency for a second and start with a very large model. Like we will call it base large model, right? This model will perform very well, but it will be also very slow. We want to do that because we want to explore the upper bound. Like, what is the upper bound if the efficiency were not a concern? Like, we don't care about latency. Let's try to optimize the driving score. Let's focus on driving first, right? To do that, for example, let's take this winner of Carla Autonomous Driving Challenge 2.0, LLM for AD or Carlova. This work was called with both names. What does it do? It starts with a large vision encoder, a VLM or MLLM, to extract the features, and then feeds these features to a transformer decoder, the action model, to predict the action, also condition on some speed and target waypoints. And what we do is we process the image exactly like this model by dividing it into two patches and then applying 2x2 spatial pooling to reduce the number of tokens. Okay, we have a very similar design and we call it base large model. There is only one difference that we, like a small trick that we apply differently than Karlova. What happened is that when we visualize the attention maps, we saw that the model struggles to focus on image patches that are relevant to action. Like there is no alignment between the image patches and the action. To align this, to align the action with the observations, we compute the attention between patch features and the action queries. This gives us a mask like this. This mask shows on the image where the ego vehicle is likely to drive. And you can supervise this, right? You can take the expert actions, project them onto the image, and supervise this mask to better align the action with the image features. So what is the performance? We benchmark it on the Carla V2 bench to drive. This is a closed loop benchmark, quite challenging. What we found out that compared to the previously best model, it improves the driving score by 10. So this is a very large improvement. This is nice, like that. It outperforms the previous best performing model by a large margin. But we think the other axis that we need to consider here is the latency, right? When we look at the latencies of these models on the right axis, we see that the best performing models have latencies in the order of hundreds of milliseconds, right? What does it mean? 100 milliseconds is 10 frames per second, and our base model is not different. It achieves the highest driving score, but with a latency of 120 milliseconds. This roughly corresponds to 8 frames per second, which is very low for real-time control. Let's say we are happy with 25 frames per second, right? This corresponds to 40 milliseconds in latency. You see this orange line, which is the 25 frames per second line, and almost all of the models are above this line. There is only one model which is below, and it is ADMLP. If you know ADMLP, it is proposed as a sanity check, and it's not like a real planner. So this is the case. The best performing models have high latencies. We also tried different large models, like a bunch of them. Here, this is our base model. The radius of the circles here shows the size of the models. What do we have? We have the smaller models to the left and the larger models to the right of the one that we used by default. So we tried mostly smaller in size because we were hoping for a better latency. And if you've small, like similar or larger in size, to see if we can actually improve the driving performance further. What do we see here? The same story basically, right? As the latency goes down, so does the performance on the left. Also, the best ones with a driving score above 70 have a latency greater than 100 milliseconds. So we didn't achieve anything because 100 milliseconds, as I said, is less than 10 frames per second. One small note here is that the bigger models that we tried did not improve the performance. It could be due to underfitting. It could be that we didn't train it long enough or we couldn't find the right setting, but also it could be due to the expert performance because we have seen other models that achieved driving scores greater than 80 with a different expert like PDM Lite. So I leave the small note here. But going back to the initial concern of efficiency, for efficiency with large model in embodied systems, there is this dual approach, which has become quite popular. You probably heard about Daniel Kahneman's Thinking Fast and Slow book. So he proposes the System 1, System 2 framework, where we have a small model for fast reactive decisions and a large model for better but slower decisions. Right? This is also applied in driving. There is this great work, LeapAD, which came out last year. What LeapAD does is it has this memory bank at the bottom, as you see. It uses large model. The large model gives you reliable decisions, right? Then it stores these large models' reliable decisions for very complex cases in this memory bank, right? And the small model is only used to retrieve these relevant instances as needed. Retrieval is fast, so small model will retrieve these instances from the memory in a fast manner. So this is a very cool idea, but unfortunately it's not evaluated in the closed loop setting, probably due to runtime constraints. Also, conceptually, memory might be tricky to manage in dynamic systems. Like it will be expanding as you encounter different situations, and to achieve generalization might be tricky here. So we focus on the speed axis, right? What does it mean? Like we have the small model, large model, and we have the time axis below. What will happen? Small model will finish earlier than the large model, right? It will take less time to compute. And what happens in a typical dual paradigm is that we can use the large model infrequently, right? We can use fast model at every time step maybe, but for the large model, we can only use a fraction of time, right? Because it is slow, right? So our idea is actually, what if we start computing with the large model earlier, right? What if we start processing the previous time steps frames earlier? That's why we call it thinking ahead, right? Efficiency thinking, through thinking ahead is we will start processing the frames with the large model earlier. How can we do that? We can batch multiple time steps in the past time steps and process them with the large model in parallel. What did we achieve? We saw that t minus delta time step can be available for time step t. This way, we can benefit from the large model at every time step, right? What will happen is that we will always have information from the large model, this reliable information from the large model, although it is a little outdated due to the time it takes to process the input with the large model. We will need a forecasting mechanism to update this reliable but outdated information from the large model in the past time steps. Let's look at it a little more in detail. Given two frames delta apart in time, we have image at t minus delta and image at time t. We have two models. We use the large model to process the previous frame, and we use a small model to process the current frame at time t. This gives us features from the large model at t minus delta and features from the small model at time t, right? Now, based on this previous frame's features from the large model, along with some conditioning input like speed and the target point and previously predicted action, we will develop a forecasting module to predict the large model's features at the current time step. Now, what we are doing is basically, we have this reliable information, which is in the past. We bring it to the current time step with this forecasting module, right? It uses some conditioning and previously predicted action to predict the features at the future time step, right? Now, we have the features of the large model predicted at the current time step. We have the features from the small model, and we again have some conditioning input. Now we can predict the action given this information. As we did with the base model, we also have this action mask, right? We still have this alignment problem between the actions and the observations. So like in the base model, we supervise the action with the expert action. We supervise the action mask by projecting the expert action onto the image. We also supervise the forecasted features using the large model's features at the current time step, right? Because we want these features to correspond to the features that large model would give us if it was evaluated in the current time step. The tricky part about running the large model at the current time step, it will be slow, right? But it's okay because we have to do that only during training. We don't need the supervision or loss function during inference. So we can still be efficient during inference. This will only affect the training time. Now, we have this model, we call it Async model. Let's compare it to the base model. What do we expect? We expect it to be a little worse because now we don't have reliable information from the large model at every time step, but we expect it to be also faster. And this is exactly what we see here. The last two ones, base model achieves the highest driving score, which is around 74 with a latency of 120 milliseconds. And Async model to the right is a little worse. It is 69 point something, like it's -5 compared to the base model, but it also reduces the latency to 50 milliseconds. 50 milliseconds is 20 frames per second. We hesitated to call it real time. I think it's fair to say that it's near real time, but it is impressive because the Async model achieves this without having access to the large model at the current time step. It still performs very well, ranking second after the base model. Now, what is missing? Why do we not perform exactly like the base model, or like what contributes to the performance? Do we really need the large model? Do we really need the small model? Which ones are important? Like what is working, what is not working? To understand which parts contribute to the performance, we analyze the model by removing certain parts, right? Now we converted the order. We start with the base model, then we see the Async model. Here you see some metrics like driving score, success rate, comfort, all higher, better. These are official metrics used by the bench to drive benchmark. Now let's start by removing the forecasting supervision. What we have, we still have the forecasting module, we still have some additional parameters on top, but we don't supervise it to predict the future because it could be just additional parameters, right? We know that scaling helps. And to test if actually forecasting is useful, we remove the forecasting supervision. What we see here, without supervising forecasting, driving score drops to 54 from 74. So it's a large drop in all metrics, which tells us forecasting is important. Forecasting really helps the model to achieve high scores. The next one is the small model, right? This reactive ability of the model. What if we use only forecasted features? If forecasting is so helpful, right? Let's remove the small model and continue with just the forecasting. Without the small model, the performance is even worse. It drops to 42. So we need this up-to-date information from the small model. Small model is our only chance to peek into the current time step, right? And we actually looked at the specific skills that we lose when we remove the small model, and we saw a significant decline in emergency braking, for example, which makes sense, right? For emergency braking, you need current time step input. And then we tried the action mask, which was a little surprising. This small trick helps so much because without the action mask, we see significant performance loss. It is important to provide this extra supervision by aligning the predicted actions with the observations. The last one is, what if we don't have the forecasting module at all? Like we only have the small model without forecasting. This is surprisingly good. Like only having the small model at the current time step, it shows quite good performance. But what we observed is that there is like notable declines in overtaking or emergency braking abilities. And we think that it's because large model helps the small model. Large model provides strong features for predictable scenarios. If you can predict it, large model can handle it. And this enables the small model to focus on detecting deviations, such as these emergency cases and so on. Lastly, we did like a small experiment to figure out what is missing in the async model. What if we had perfect forecasting? What if we use ground truth features for forecasting? Can we catch up with the base model? And the answer is yes. If we use ground truth forecasting features, we again achieve a performance of 74. This is actually quite similar to where we started from. So forecasting could be improved. This is what it tells us. In addition to this, we looked at some specific skills to see that where does the model improve the most or where does it fail. We see that the async model can catch up with this large model, base model, in scenarios like overtaking, emergency braking, and yielding. But there are large gaps between the base and the async model in traffic sign handling and emerging scenarios. But of course, another important axis is here, FPS frames per second is increased to 20 with the async model, which is much better than anything out there in the benchmark. Here I have a video comparing the performance of the model async here. If we don't have the small encoder, it crashes into the vehicle front, right? So async model can do this sudden brake thanks to the small model that it has. This reactiveness to the emergencies can be observed in the video. And we have another sequence where we compare async model to the without forecasting. So here there is an intersection and there's this sudden red light change. Async model can react to this and stop. And then can take the turn safely after the light turns green. When we remove the forecasting next, the same scenario, sudden red light change, it fails to react in time and results in a crash. What is missing? An immediate improvement. We need to focus on the forecasting because we saw that using ground truth features brings the async model to the level of the base model. And we also want to figure out how to use larger vision encoders because this could enhance both perception and decision-making capabilities. Changing expert might be useful, right? We might be upper bounded by the expert performance. So if we try experts like PDM Lite, we can actually increase the upper bound for the model. Also, as I mentioned, we don't claim real time. It is, I think, fair to say that 20 frames per second is near real time. Improving runtime further would be quite helpful. So this is the first part that I wanted to talk about. Now I want to talk about rewards a little bit. RELACS. This is a name that my student RI came up with. This is joint work again, RI, Shadi, and no, Chonghao is not included this time, sorry. Hongyang's team, different people. So why do I want to talk about rewards? Because when we look at the research in self-driving in recent years, we see that shift from perception to end-to-end models, right? Instead of solving perception tasks like segmentation, mapping, detection in isolation, the trend is training agents that can plan, reason, and act all the way from sensory input to the actions. So here you see the figure from the Apple's GigaFlow, right? I guess everyone here has seen this. Self-play improves, I forgot the exact name of the paper, but this is quite impressive work which uses RL agents in their in-house simulation by driving against each other, play against, or not playing together, I don't know how to call it, they can learn perfect driving behavior, right? So this was quite impressive to see this year. Right now, the progress is mostly in simulation, but with the progress in, for example, world models, maybe soon we will observe these kind of agents in real world-like environments, right? One attempt in that direction is NavSim, for example, is quite promising. So when we have planning in mind, one of the important questions is, how do we guide these agents, right? What kind of feedback do we provide to these agents so that they can learn from it? I'm talking about reward functions if you're doing reinforcement learning, for example. It's because it's very hard to define what is good driving behavior, right? We need to consider many things like goal reaching, efficiency, comfort, safety. Even in a very low level, we need to consider the exact position of the vehicle on the road, like orientation, etc., right? This requires some hand design rewards. We have seen this earlier in papers like implicit affordances, Roche, and so on. These are RL agents that first came out with Carla V1. And to compute the reward, which looks like this, we need ground truth measurements. Ground truth measurements are okay if you are using a simulation like Carla. But if you want to scale it to real world, you have to come up with a way of obtaining these measurements from the observations, which is quite tricky, right? Let's say you are predicting the orientation of the vehicle to compute the reward which you will use to guide the agent. This is, if you do it wrong, you will give wrong feedback to the agent, right? This is quite important. Another thing which is very annoying is these reward functions have multiple terms, right? In the objective function, we have to consider position, goal, rules, collision, comfort, and so on, and you have to weight them, and then you have to tune each of these weights very carefully, right? If you ever trained an RL agent, you know what I'm talking about. It's quite annoying to come up with weights like this. In this Apple paper, for example, self-play paper, they start agents with different weights. Some of them focuses on the goals, some of them focuses on safety, and so on. This works well for them because that's exactly what they want. They want diverse behavior from agents in the simulation. But if you have a single agent to train, this is quite tricky to figure out the right weight for each component. Designing and balancing them is quite painful. What is the alternative? Is there an alternative? Yes. In robotics, an alternative is explored to learn reward functions directly from observations. Given videos like this, you look at the behavior, it stops, although opposing reactions, right? The first one is good driving behavior. The second one, there is a crash, so it's bad driving behavior. If you can just figure out the reward by looking at the video, it's great because then you can scale the agents to large-scale real-world environments without manual reward engineering. We want to get rid of manual reward engineering. We want to figure out the rewards by just looking at the videos. This is closely related to a task, video prediction task. Why? Because in video prediction, what we do is we want to predict the future, which is resembling the features that we observed in the training data. Expert-like features, we will have very high likelihoods when you are doing future prediction. And if the future predicted has low likelihood, then it means that it is a low reward situation, right? This is a very basic common assumption, which has been first explored by Viper in 2023 in the robotics domain again. When predicting the next frame, if the next frame has low likelihood, then reward should be correlated with that low likelihood. That is the basic assumption. Very recently, it is also explored in driving with diffusion models, VISTA in 2024. Here, the idea is that if the multiple features predicted by the model do not agree with each other, in other words, they have large uncertainty, then it is a sign of out of distribution. If I predict very different features with a generator model, diffusion model, then assign a low reward, right? Quantify uncertainty as the standard deviation across predictions by the generator model, and then use it as a reward. Now, given these two ideas, Viper and Vista, let's think about different situations. For example, the expert videos from New Scenes, right? New Scenes is expert driving, perfect driving data set. And there is this crash video. I'm sorry if it is sensitive for some of you. Now, these likelihood-based models like Viper and Vista will work in these situations, right? It will correct the Vista and Viper will correctly assign high scores to the first one and lower scores at least to the second one. But what happens is that the uncertain does not necessarily mean low reward. There are some inherently uncertain situations, like turning scenario here in the third row, right? If I'm turning, I don't see what expects me when I completed the turn. So there will be high uncertainty, and these models will assign low score to the situation because of this high uncertainty. But we don't need to penalize the model with a low reward in this case, right? A high uncertainty does not mean it is low reward, does not necessarily mean low reward. This requires thinking reward prediction separately from the future prediction. That's why we propose this dedicated reward model independent of the future prediction. This is like a separate dedicated reward model to predict the rewards directly. What kind of rewards? Rewards directly related to driving, like driving score, distance covered, and so on. I will go over them in a second. These are basically quantities based on data that are used to evaluate the driving agents on Carla. If we have that, we can actually assign high scores to even highly uncertain situations. When we use likelihood-based models, what happens is that they are trained on expert driving behavior, right? In data sets, what we have is mostly expert driving. Because this is exactly what we want our future prediction model to learn, right? To learn the expert driving behavior. When they see suboptimal or unsafe driving behaviors, such as traffic light violations, some crazy maneuvers or collisions and so on, future prediction becomes quite unreliable, right? They will not work most of the time in out of distribution situations. But we need to be able to assign low rewards to these situations. The question here is that how do we learn what should be low reward? Because a reward model is expected to recognize the crash scenarios, for example, as low reward situations. We don't have data for it. We collect it. We go to Carla and collect counterfactual data. Starting from the same initial state, we try different actions. What do I mean by different actions? We have the expert driving, which is great. It doesn't make any mistakes. It just drives through the scenario without any crashes, right? And then we execute some crazy decisions like turning left, going out of the road, or turning right, causing a crash into another vehicle, and so on, speeding up. These kinds of various decisions, which results in diverse reward situations, right? It's not only very good driving behavior, but we have the suboptimal driving behavior because of these random actions that we try. What are we going to do with this? We will get this counterfactual videos, right? These are like video segments which are sufficiently long. What do I mean by sufficiently long? They have like this crash scenario completely observed in a segment. We first encode them using a frozen video tokenizer, Cosmos, from NVIDIA. What Cosmos does, Cosmos gives us some compressed tokens at varying spatial temporal resolutions, and then we flatten them and feed them to a transformer decoder to process this sequence of tokens causally, and then predict some driving related quantities. Let's go over them. Like, well, how do we specify the reward? First of all, an obvious choice is driving score, right? This is how we evaluate the driving agents. Driving score is composed of route completion and infraction penalty. Let's start with the route completion. Route completion is the percentage of the route completed. You have a route to complete, like you have a goal from A to B, and what is the percentage of the route that you complete? This requires some like knowing goal location, some map, etc. We don't want this kind of dependency in the reward function. We wanted to only consider the distance covered. So we convert it to distance covered by multiplying the route completion by the known route length, okay? Now we are gonna predict the distance covered by the agent. The second one is infraction penalty. Infraction penalty starts from 1, like ideal infraction penalty is 1, and then it is decreased with some ratio depending on the crash type. For example, 0.5 for collision with pedestrians, or 0.6 for vehicle collision, and so on. And multiplying these two gives us the driving score. We will predict both of them, distance covered and infraction penalty. Now, these two look at the video and then predict something related to what has already happened, right? But in a crash scenario, what is important also is predicting this earlier, right? Important to be able to assess the states leading to low reward outcomes. This is like the value of a state in reinforcement learning, to recognize the risky behaviors early on. Let's say there is a crash here in the third segment. We define the state value, which incorporates future infraction penalties, right? If I have a crash in the future, I want to be able to start decreasing my score early enough, right? By multiplying the infraction penalty of the current segment with the segments in the next two time steps, we can actually start decreasing the score earlier. You compare the infraction penalty, which is red, state values start decreasing earlier, meaning that we can anticipate the crash, right? This is a very important capability that we want from a reward model. Lastly, we want some explainability. Okay, there is a crash, but what kind of crash? We add some lightweight binary classifier heads to predict the presence of an infraction type in a segment. This is for the predefined set of infraction types on Carla, as you can see here. Now, okay, let's see how does it perform. First, we validate it on Carla. We take the clips. This is validation set, very similar to the training. So we are kind of evaluating the ability of in-distribution. We group the clips into 6 categories based on the ground truth scores, ground truth state value scores, and we compare to likelihood-based models that we mentioned, Viper and Carla. What we want to see here is that we want to see a steady increase, right? Because a score of 0.02 means that there is a crash, as you see on the left. A score of 0.4, 0.6 in the middle, there is a crash, but not as severe as the 0.2. And then a score of 1 means that it's perfect driving, right? So it's a score between 0 and 1. 0 is crash, 1 is perfect driving. And there is like 6 categories in between them. And we want to see in the predicted scores by the models, we want to see a steady increase in the scores. When we look at the scores predicted by Vista and Viper, they are mostly the same, remains the same. Viper is a little better, but still not convincingly increasing. With our model, we see this consistent increase across the categories, right? This captures the gradual differences in driving quality, which means that if there is a crash, you can separate it from the expert behavior. And moreover, you can actually capture these gradual differences between different driving qualities. We also check the correlation metrics between the predicted and ground truth scores. Here, higher correlation means that the scores predicted aligns with the ground truth. And I think it's a bit hard to see, but on the video, we also show the scores. Okay, Carla is easy, right? You have a supervised model and you are training it on Carla, testing it on Carla. This is expected, I think. Like, it's not so impressive. What is impressive is that we took this model trained on Carla and tested it on new scenes. New scenes expert driving, right? Expert driving should be scored high. And what we see here is that the scores that are predicted for new scenes videos is relatively high, right? It needs to be high, but compared to the Carla videos, for example, that like each model here needs to be checked relatively, right? Because the baselines produce unbounded scores. We don't know what 0.3 means for Viper. It's a likelihood. It is hard to judge the baselines. So we need to compare them within the model's results. Ours is grounded in Carla. Look, if we predict 0.6, it means that vehicle collision. And if we predict 0.9, it means very close to expert driving. So this is good. New scenes works. But what is also important is, does it generalize to real-world crash videos, right? If we give it a driving video where there is a crash from YouTube, some random video, will it score it high or low? This is the tricky part. There is no data set like that, right? We went to YouTube and then downloaded some videos with this diverse range of road conditions, environments, weather settings. It's a very small data set, 84 videos. We annotated it as expert, crash, and near crash. Okay, you see the crash on the left, near crash in the middle, and the expert on the right. What do we expect here? If you have a reward model, expert should be scored higher than near crash, and near crash should be scored higher than crash, right? We can compute the correlation metrics according to this ordering between the 3 categories. Here, baselines produce very similar scores for each. ours can clearly distinguish between these three categories. Increasing the reward predictions from crash to near crash to expert, you can see that also in the high correlation metrics, coefficient values, sorry. Here the scores, crash, I will read it for you. Crash is scored as 0.26, near crash 0.62, and expert is 1. Right? This is exactly what we want to see. We were curious, like, how does it generalize, right? We trained it on Carla and tested on real world, and it still works. We suspected it's because of Cosmos tokenizer. If you know Cosmos, it is a spatial temporal tokenizer trained on large amount of diverse data, both synthetic and real. And we replaced it with Dino, right? What if we just use Dino version 2 as like an image level tokenizer? We found that our model with Dino performs similarly well on Carla and new scenes. But when we check YouTube car crash, it was not the case. This suggests that maybe generalization is harder in out of distribution situations and suboptimal behaviors that we have on our YouTube video. We did another interesting experiment. We took, you know Navsim, right? We took a video on Navsim environment, and using a 3D Gaussian splitting approach, we made it go slower or faster, right? We first made the vehicle go faster or slower than the expert to see if this is captured by the distance covered metric, right? We predict distance covered. It should be that slower one should be 0.19, let's say. Then the real one should be higher than this, 0.29, and the faster one should be higher than this, 0.38, and that's exactly what we observed. So actually, we can measure the distance covered. This is good. Another thing we did, we took a real video on the left and made it go out of the road, right? Caused this deviation off-road scenario. Now, what we should see that state value should score the real one higher. And this is exactly what we see. Real is 0.79, and the off-road deviation is scored lower as 0.61. So this is good, right? It can actually detect the deviation. Now, I want to mention some remaining problems. When we collected this counterfactual data, what we realized that it's very hard to cause a certain type of crash. We observed a significant imbalance in the crash types. We hope that future work can focus on some data augmentation technique maybe, or some infraction generation, or some active data collection to address this imbalance in the crash types. Also, infractions are very sparse. They happen like in a few seconds somewhere in a very long video. It might help to work on infraction localization, like people doing action recognition, action localization. And of course, an obvious next step is using this reward model in a real-time closed-loop planner, like training an RL agent with our reward model is the obvious next step. Thank you very much. I hope I didn't take too long. While answering the questions, I leave you with this nice video showing the results of the RELACS. Yeah, that's it. How did I do the time? I don't know. Thank you.
Thanks for Professor Fatma's talk. Any question from the audience? Okay, I actually have a question for you.
Yeah.
So I think it's a general question, like we want to inject what we call reward model to current planner, so that we want that the reward model could be some kind of evaluator of the scenario, so the planner could get information prior to that. So what do you think about the generalization of the proposed reward model in your work, saying that, okay, if you given different scenario from nuisance to Waymo, or even to lift some older data set, does it gonna be generalized well, or does it depend on the domain you train, or it is like a universal applicable reward model?
I mean, I think YouTube is more tricky than any of the data sets that we have, so I am quite hopeful. But relatively, it might be tricky. It might be the case that we didn't show it a certain type of failure and it doesn't recognize it as a low reward situation. But if it is a crash type, like vehicle collision or pedestrian collision, stuff like that going out of the road, I think this can be handled. Like Cosmos tokens are enabling the model to see the same latent representation and recognize the crash type. But if it is like a very OOD situation, I don't know, hitting some animal, even that might be similar to hitting a pedestrian. I'm sorry for this, but like, I'm not sure, but I'm hopeful.
Okay.
Put it this way, yeah.
Okay, thank you, Professor.
Thank you, Chantal.
Yeah.
Thanks, everyone.